Hello, and welcome to yet another data science seminar. And this time we're focusing on the topic of AI and art. So whether art is still just for humans or also for AI. So obviously, if it were AI doing art and AI judging and enjoying art, there would be no problem. But we are now at the intersection of AI generating art and previously, obviously, looking at X-rays and determining the diagnosis of people, driving cars, handling text, speech, images, and everything. And now we've moved on to AI. Still, the world has both AI and humans at the same time, and this is the main source for difficulties. So today's 4 presentations will introduce to us 4 examples of AI trying to produce art. Or is it? So let's find out. I'm glad to introduce the first speaker, Anna, who is the founder of AI Norn. And she graduated Mehmet at the Moscow State University and has worked as product manager in several large Russian companies such as Yandex, Rambler, and Mail.ru. So please, Anna, the floor is yours.
Thank you. Hello. Today I will tell you about the project at the intersection with data science and art. The name is AI Norn. AI Norn can create art like a human does with stroke and brushes and real paint. It works in its unique style. We call it neo-impressionism, and I will tell you how we set the problem and how we solved it. And I want to raise a question about if a programmer can be considered as an artist. So how it works. You can just upload any picture in our software and get a pre-calculated simulation of painting process. And if you're okay with it, you can run a real painting with robot. Later, we will show you how it works. During the painting, the program corrects itself using computer vision. There's a camera in the top of the robot. Painting process looks like this. So camera takes several pictures of the canvas and compare the canvas pictures with model picture and calculates several roads and colors and paint new layer. Then it repeats and repeats until the stopping criteria. About robots we use. We took with us just a small robot, but at home we use a combined machine. We built a robotic platform based on Arduino. It works in sync with the robotic arms to paint bigger pictures. So also we have integration with a big industrial robot, cooker robot. We don't have it, it's very expensive. It's our friend's robot from different city, and here to the picture, it paints portrait of Van Gogh with our algorithm remotely. So I wanted to show you how the simulation looks like, but we have some technical issues. So without simulation, we just run robot and start real painting. Can you try to start it? Now it's calculating the first layer. It usually takes several seconds. It was a surprise. I hope to show you by the video, but it's a picture of Tartu University. Okay, I will continue. I'm not so lucky today. So the painting process takes time. So in our time, we didn't finish it, but you can see the beginning of the process, maybe 1 or 2 layers. So after it paints the first layer, camera here will take pictures, and after that, the model will find new roads and new colors for new brush strokes. And it will repeat and repeat those layers. So, a little bit of luck. And here's the result of simulation. So the painting will look like this, not the exact, but close to. And this was the original photo from your Facebook group. Okay. Let's go next. So about the problem. The easiest way to paint with a machine is to pick point by point and move to canvas. But it's too easy and not interesting. At the left side, there are examples of such painting style. At the top is offset printing, and in the bottom it's pointillist Syrah painting. And for a human, it is quite a hard task to paint like this, but for machine it's obvious. And what we wanted to do is present it on the right side. At the top, it's the Van Gogh painting, and at the bottom, it's a piece of our painting where we tried to achieve similar effect. Another big part of our software is the color mixing model. The problem is that we don't have time and space for pre-mixing all colors we need at the painting. So our model do mixing colors right on canvas during the painting. So one brush stroke, it takes red color, another brush stroke, it takes yellow color, and in average, we'll get orange. So the mixing process works with a small palette with from 6 to 10 colors. The example is here. But after a couple of hours of painting, the palette looks like this. So it's not really clean, usually. If summarizing the task for our robot, we call this style near-impressionism, and the formal problem is to make brush strokes follows shape and texture of original picture, to mix colors right on canvas, to enrich colors, to get more colors than it was in the original photo, and make the image recognizable but not like a printer. There are some examples of photo prototypes and the result. It's photo of real painting, so of course cat. It's Isaac Asimov because of robotic claws. Here you can see we get more colors than it was in original photo. Like penguin, house, and the horse. Where is our horse? It's right there. So, of course, we're not the only one robot artist in the world. There are several projects, different robots, different styles. And as we see, it could be infinite styles and techniques and algorithms for robot painting. There are some other experiments with different techniques we tried to. Little bit. And it's not necessary to use a photo at all, because a neural network can imagine it from nothing, like an example here. So we have this painting with us. I can take a closer look later. So if we talk about robotic painting in total, what we want to do is to build a platform where different painting algorithms can be combined and work with different types of robots. So, and this software we want to be open sourced. So you, as the author of algorithm, you have your own algorithm connected to this platform with easy and standard protocol. And the same for different types of robots. We work on this platform, and we have some prototype and going to launch it soon. Hope we made it. In this case, it could be a decentralized painting system where authors of algorithms, robots, and maybe even customers are all over the world. Okay, it's another example. So what we did, we believe advantages of this technology is that you can just plug and play any photo. So you don't need any pre-calculation or any manual computing. We use classic materials and mediums. It's just acrylic or oil painting and any flat surface to paint on. And it's equipment independence. You can use any robotic arms or even not arms. And it's standard protocol we use for to communicate between algorithms and robots. So it's a it's a really tiny team, just the two of us, Nikolai and me. We hope this team will grow up. And thank you for listening. And we'll be happy about any feedback. So that's it.
Thank you very much. So, does anybody have any questions to Anna? Please, Eduard.
Thank you for the presentation, but something is not clear for me. What are you using inside your algorithm that paints? Is it style transfer? Is a deep learning style transfer thing? That, for example, you paint a photo using the style of Van Gogh, or are you using something more deterministic? I don't know.
Okay, we have two main models, one for roads and another for colors. And at the top, there is algorithms which, for each painting and each layer, it finds the best parameters for those models. So we don't use any existing ready models. We made it by ourselves. Roads model and color mixing model are it's just a little bit of math, not neural networks, but the model which found parameters, it is a neural network.
Thank you. For that neural network, just a follow-up to Eduard, do you use any data? I mean, since we're at a data science seminar, does it learn from other paintings, or what kind of learning does it go through?
It's learning by itself. So it's learning, making simulations and compare with original photo. And so it doesn't use any other paintings to study. It study by itself from comparing simulation of picture with original.
So I have many more questions, but I should let others ask. Jaak, you had one?
So thank you so much for the presentation and everything that you do in here. I would be so happy if you want to get more people involved, you should run a special course with a dedication to this kind of development. We could facilitate you, help you to do that. But my question, and I bet you get that a lot, is how do you define art?
I'm sorry, I didn't get the question.
How do you
define art? It's art, artist. How do you define art versus, I just copied this image in this style?
So is your robot a painter or a printer?
For us, it is a painter because Okay, if we do a printer, we do it like a printer, point by point. But we don't do this. If you take a closer look, you can see that our brush strokes has form.
This was not a criticism that you have to
Yes.
address kind of in this way, but
Yes,
in more general terms. Of course, artists also move out to the nature and say that I will just paint this into my canvas. You could set up a performance where you go out and say that I have a camera and you paint it. And you can do the performance outside. But still it's sort of like framing the objects or something. What is the creative part? I think you have to think about that.
Yeah.
I wasn't criticizing, but just
Yeah, I understand. It's hard for us to answer those questions because we are not artists. We like engineers, so it's a hard part. I agree. But for what we want to tell to the world, that algorithm, that math outside, inside this program can be told art itself. So the art object is the algorithm, because then we created it. It was a lot of creativity, and it's not deterministic problem we solved. So it can be solved in many different ways, and the problem can be formulated very different. And all this together for us, this is art, not the canvas, not the canvas, it's algorithm. That's how we see it. But we're engineers, so we biased, of course.
You're lucky that you're in a house full of not doctors or drivers or language or other artists, but actually engineers. So we rename ourselves into the Faculty of Arts because, well, but you convinced me at least. Does anybody have a last short question? Lisa?
It might not be a short one, but perhaps is it at all useful to use digital paintings as a way to design these algorithms, or to have data about how actually, in a digital sense, paintings are composed? For example, when people use like those digital tablets to paint, is that a useful data source in this field?
So can you record the process of a human painting, not with colors, but, you know, on a tablet, for example, if that's what you mean, and then learn from that and imitate their style?
In future, we hope to do this because it's like, yes, it's possible, but we didn't try it yet because we need. It's need to be a little more programming for that.
Okay, well, let's thank Anna again. Thank you very much. And millal me seda teeme, pausi ajal või? Aeg, sa käskisid seda rangelt valida. Ahah. Very nice. Nii. Yeah, can we keep it?
Yeah, of course.
Thank you. So nice.
Let's put that on the blockchain and
With the NFT. Я понимаю, вы хотели еще кого-то нарисовать или это отдельно? Аннет говорит.
Ну, это завтра.
Хотите объявить? Или отдельно?
Окей. Tomorrow will be exhibition opening on Institute of Physics at Physicum at 5 o'clock. So we are going to continue this painting there. So if you like, you're welcome.
Okay, thank you very much. And as for our seminar, we move on to our next speaker, who will be Eduard Barbu. So Eduard is a research fellow here at the Institute of Computer Science. And he has a long track and experience in both academia and industry, and has worked in Italy, Spain, Romania, and now Estonia. And he specializes in ontology, well, several areas from NLP, including ontologies and text summarization and others. And so we'll see if he can convince us if his work produces art. So, Eduard, the floor is yours.
Hello, everybody. So my presentation is called Devices to Compute Human Creativity. And I want you to convince you by the end of this talk that the human creativity can be computed. Is it? Okay. I will start with an overview of the presentation. I will talk about the problem of human creativity and the fact that no long time ago it was thought that computers are not capable of creativity. Then we move on of what I think is the main part of this talk. It's about poetry generation. I will introduce the basic of generative modeling in a very intuitive way. And I will talk about, again, very intuitively, about two devices to compute and to generate poetry. There are recurrent neural networks and transformers. And I deem this of being a semi-successful approach. You will see some examples. One was created by myself in a very naive way, and the other one is close to the state of the art in the field. So there are steps in this direction of generating poetry, and with good it's a semi-successful approach. Then I move on at the third problem. It's about generating painting descriptions. It's about bridging the gap between low-level concepts at the level of painting and high-level painting concepts. We would like to have a painting and to replace a critic of art. So an algorithm will generate a description for that painting using high-level concepts like the meaning of the painting, the emotions, and so on and so forth. This is an open problem. There were many different approaches. The best one combined ontologies with some deep neural networks. It's an open problem. It's not solved. Very few people are working on this. If there are students here in audience that need a thesis about this, please contact me after that. I was not successful until now to involve anybody. Everybody abandoned this problem. It seems to be very complicated. So I will start my talk with an interview that Garry Kasparov gave in 1989. He was asked by the interviewer, I will not read everything, but he was asked by the interviewer if a computer program can beat him. And he was very straightforward, saying ridiculous. And part of what I think it's important for this talk is when he says that when I say intelligence, I also mean intuition and imagination. These are related with creativity. And at that time, which was not so long time ago, was thought that computers cannot have. Can you see a machine writing a novel or poetry? Of course, in 1989, it was impossible to think, unless you were a science fiction writer, that this could be possible. Fast forward, Lee Sedol was one of the best Go players in the world. In 2016, some month before the match with AlphaGo, he was asked if he has chances. He's not so straightforward like Kasparov, but he thinks he has chances in the match. The third character I want to introduce is David Cope. Maybe in the next talk they will talk more about him. It's a guy that I admire. It's one of the pioneers of artificial intelligence and music. He was asked if the computers are creative. This is an interview 2-3 years ago, and says, oh, there's no question about it. Yes, yes, a million times yes. Creativity is simple. Consciousness, intelligence, those are hard. So the opinion for the most part of 20th century was that creativity is related to consciousness and intelligence, but nowadays few people believe this is the case. The outcome. In 1997, 8 years after the interview, Kasparov was beaten by IBM Deep Blue, and Lee Sedol was beaten by AlphaGo. So clearly the machines are better in these games than humans. Relating to artificial intelligence, the DeepMind AlphaGo algorithm was innovative. It combines tree search with deep learning network that learns from previous game, but the algorithm that beat Kasparov was not so novel. Was using brute force and some parallelization. I'll move to what I think is the main part of this talk. It's about generative modeling, and I give a very intuitive way to understand the framework. So basically you have a data set of observations that can be pictures, poems, any kind of text. And the premise is that the observations are coming from a known probability distribution, and you want to learn a model from the data set that will approximate that probability distribution. And the examples that you generate should be like the data set, but also different from the observations in the data set. This is best understood if we look here. So on the left side, there are pictures of real people. Then you get a generative model that puts some perturbation, and you get the people from the right side that are like the real people, that no one is real, really. The generative model has a lot of applications. One that I like in particular, other than automatic generation of poetry, is automatic generation of music. David Cope is again the pioneer here. It created experiments in music intelligence. And if you go on YouTube, you'll find a lot of video uploaded where he generates music in style of Bach, Vivaldi, Prokofiev, Bartok, or Mozart. In particular, I have a link here of music in style of Vivaldi. I think it's a mind-blowing experience. I thought it was the master himself that composed that piece of work. Related to automatic generation of text, the same framework is used when we want to write automatically stories, poetry, or novels. The novels are not so good because after a while they do not make much sense. What are the properties of text that we want to model in this framework? There are 4, I think. One that is that the text data has a temporal dimension, not a spatial one like pictures. Then the order of words matters in text. John loves Mary is different from Mary loves John, and some sentences are nonsensical, like mend the apple with. The language, unlike the pictures, are sensitive to change. You change a word, the meaning is changing. You change some pixels in an image, there is no much difference to the object in the image. And how people try to solve this is predicting the next word in the text. This is very simple. So if you start with a string and you can predict the next word always, and this makes sense, that solves your problem. At least these are the state-of-the-art algorithms. People have tried different architectures for this. Nowadays, the deep neural networks are the state-of-the-art. They started with recurrent neural networks that basically you see here. they propagate the context from a word to the other. And the problem with them is that the signal from the early sequence fades away. So when you arrive at step T, if the step T depends on step 1, that is very unlikely that the network will learn this. And after that, the next step was to move to LSTMs that are better for long distance dependency. Dependencies you see here. An example of, can I have a laser? This is the laser. So in this sentence here, the man whom I seen yesterday after lunch in front of the library when fishing, went depends of the man, right? The man is very at the beginning of the sentence and does not depend on library front or the. So simple models cannot model this. So how the poetry generation is working, like any other generational algorithm, you start with the corpus. Oops. You start with the corpus, which is a collection of texts or poems. Then you split the sentences, the corpus into the sentences. Then you generate input sequences or n-grams that are called in computational linguistics. Then you take everything but the last value as the feature. You train a model, and in the generation phase, you start with your own seed, and the model will generate words. This is a very simple model, but if you understand this, you understand the gist of the generation. So here is the corpus and verses. It's a nice poem by Rainer Maria Rilke called The Walk, a poem that I like a lot. As the computers are understanding numbers, here is a simple thing. Normally you start with word embeddings that are learned from another corpus, but here I just assign some numbers to the words in the vocabulary. So the key operation is predicting the next word. You see a 15, you learn that after 15 is 20, you see 15, 20, you learn there is a 3, and so on and so forth. You feed a neural network like this one that I've trained 2 years ago. And then in the generation phase, you start with some words from your own imagination, or you just pick up some words, and the network will fill it in. So this was trained by myself on a corpus of Buddhist aphorisms. They are not like poetry, but are a little bit like poetry. So as you see, the sentences do make sense if you take them separately, but when you read them together, they do not make much sense. As birds who escape the net are flying, the crows do not go to heaven. Well, the crows do not go to heaven makes sense as birds who escape the net are flying, or also makes sense, but together I cannot find a meaning, an appropriate meaning for this. Nowadays, people are using transformers for this task also. It's a deep learning architecture created by Google, and replace modeling of the context with self-attention. So basically, self-attention computes some relations between the words in the sentence and importance score. So in the examples I gave before, self-attention mechanism will find that man is very much related to went and to fishing. So as in other work, people are using the GPT-2 transformer language model that was trained on 40 gigabytes to generate the next word. And they incorporate also emotions and dreamlike structure into poetry generation, meaning that you can split a subcorpus of poetry as Bena and Kalita in 2020 have done. You split the the corpus of poetry you train on in subcorpus of poems that are about anger, sadness, surprise. And also, interestingly enough, they pre-train this model on dreams. And these dreams are supposed to give you the irrational combination of ideas that you can find sometimes in poetry, but you cannot find in the, or rarely you can find in normal language. So here are two poems picked up by myself because it still generates a lot of junk, but the sadness model, I like it a lot. It makes a lot of sense. And it's, if you know the poet, the American poet Robert Frost, it sounds like him. The last part, it seems lost place of sorrow far off. It's sort of the way he's writing poetry. Okay, so that was a semi-successful approach. An approach that doesn't work very well is painting interpretation. So basically you have a painting like Maiden Hobema, a wooden landscape, and then you want to replace a critic of art, and the critic of art will say about this painting like the foliage of trees dense and lush, the rolling clouds allow patches of sunshine to illuminate the rutted roads. How would you generate things like this? Very hard, right? So this is another painting by Jacob van Ruysdael. It's again a landscape, and he's talking, the critic of art, talking about the meaning of the painting and saying that juxtaposition of dead and broken trees with fast-flowing stream in a rocky landscape is likely an allegorical reference to the transience of life. Oh yeah, look as a computer to this and find the transience of life here. So people have tried to model this using ontologies on different levels. So you start with low-level concepts that are visual-level colors and brushwork. You have seen some brushwork in the presentation before. And then you want to connect this with high-level concepts like the painting descriptions that you have seen before. So you would get three ontology basics: basic visual level concepts, abstract level concepts, and application level concepts. And you want to learn constraints about this using machine learning. So these are different brushworks, so the computer can understand this somehow. So you see in the upper painting, it's a glassy water on a still lake. It's done with a smooth brushwork, and Joaquin Sorolla, Sea and Rocks, it's done with short brushwork. Yeah, people have tried different architectures that work when understanding some emotions, not all, but they are far away from replacing a critic of art. So I think the critic of arts they still have long life. I'm not sure about poets. They might be replaced soon. So conclusions, I think nowadays everybody thinks that the algorithm can compute creativity. Of course, creativity is different from consciousness and intelligence. And the proofs are the games of chess and Go, where the best players in the world are beaten by the computers. The poetry generation, though, needs a corpus to be trained on, and the poetry resembles the poems in the corpus, so you don't start from nothing. Maybe there will be an AlphaGo zero moment of this. And regarding to interpretation of paintings, there is not so much work, but ontology and machine learning might hold some promise in the future. So with this, my presentation ends. Thank you for attention. Waiting for your questions.
Thank you very much. So we have definitely some time for questions. There's a hand right there.
Thank you for the nice talk. So my question is like, what I feel about poetry is it should be some kind of unique thoughts which are mostly associated with your emotions. And in your case, you mentioned that we need some kind of like input to somehow like train the computer to generate some kind of poetry or all of these things. So the first thing is like, in my opinion, even though they can generate something, but it's more like any emotions or something. And if I see from the other like technical perspective, so I see like how it can be distinguished. Like you mentioned, one of the texts, it is similar to some American poet you mentioned. So how I can say that the thing robot has generated or the computer has generated, it's without any plagiarism or it's distinguished somehow from the things that are
Yeah.
in
Yeah.
poets. Yeah, this is my question.
Okay, thank you. So yeah, you raise a nice problem. Is it plagiarism or not? Well, those poems that I've showed you are not plagiarized. They are written in a style that reminds me of Robert Frost, but are not plagiarized from Robert Frost. And people nowadays are trying crowdsourcing to see if the poem makes sense, and they score the poems. They unknowingly put poems given by humans also inside, and poems produced by machine. Clearly, if you put everything that machine generates, there is a clear difference. But if you cherry pick some poems by machine, like those two, the humans are still scoring them high enough. So they don't, okay, let's say, if you cherry pick the poems, you might say that if the users are naive, the Turing test for the poems is almost passed, and you have a good algorithm based on GPT-2 nowadays. I don't know about real poets, so if you want to score this with real people and this that know about poetry, not users like you and me, that might be naive poets in their spare time.
Thanks. Jaak had a question.
I did not want to steal your question, Anna, sorry. So maybe I was not so much paying attention, but how much are you using, or how much are we benefiting from ontologies and like WordNet, etc., or is it purely statistical text without any human knowledge?
You mean the poem generation, or the other
yeah,
one?
in this kind of yeah.
No, the poem generation nowadays does not use any ontologies. It's just statistically based generative modeling using. So the best models are based on GPT-2 that you have trained on a lot of text, and then you pre-train on your task, and with some tricks.
But all the kind of random coincidences, some synonyms from the pool of ontology, some random.
No, that was an approach that was tried 20 years ago, and it didn't give us any.
Mix that this GPT.
GPT-2, yes, is the key. And I mean, it's the key in almost all the tasks in artificial intelligence nowadays. So in computer music, I think, as far as I know, I don't know, the next talk will be about this. I think they also use transformers, pre-trained transformers, and transfer learning. And in painting generation, as far as I know, also the state of the art is the same, if I'm not wrong. So if I'm wrong, someone can say otherwise. Yeah.
Have you tried to make the computer write poems in Estonian language?
I had a student who was very enthusiastic about this 2 years ago when I proposed the theme, he came to me and said, wow, it's I was thinking about this myself, you know. He came, he took, we started to do the work, and then he disappeared. So sorry. So
maybe he's a famous poet right now.
I don't know what
With a
happened
new
with
name
him.
and
So we had nice talks until I told him to make the corpus of poetry. So
But would it be harder to write poems in Estonian language?
I don't know. I think you can use the same approach as in English. You have to fine-tune it for Estonian. There may be some grammatical phenomenon and some things that are peculiar to Estonian language. But I mean, I proposed this, and I told you this was also for the second one. It was mostly the same thing. So they came and then they went away, unfortunately.
There was a question before about plagiarism. Can you make it worse by telling not just the showing not just the poem for learning, but also prepending it with a token or passing the info of who the author was, and then say, David's like, give the info now, generate something like David Frost, or generate something like Wordsworth Longfellow, or something.
I think you can do it if you have the author inside the poem. You can do it, but usually when they prepare the corpus, they don't put the author. You either make a mixed corpus from different poets, or you try to keep up the style, or you just train on a single poet. This is rarely done, but
Okay.
there are some people that try this.
Was there one last question? Yeah, please, go ahead.
Yeah, I just got a question. Do you think that this takes away from the human art of poetry at all? Kind of in line with the first question, that it is this emotional expression of something, and we've been able to teach an algorithm to put words down that seem to reflect that, yet it's missing that core component.
Yeah, of course, the algorithm is dumb. It's just a probabilistic model, has no emotions, but we can interpret that as emotions. I mean, of course, we are still far away. I mean, I said semi-successful approach, but in the future, I don't see any reason why these kind of algorithms cannot compose good poetry. I mean, already GPT-2 is writing news that are judged by humans as being very veridical. So you saw some examples of poetry that, for me, I mean, if you wouldn't have told me that the computer had written, I thought could be Robert Frost for the second one. Yeah, so yeah, that was the point, that the creativity can be computed, but as David Cobb said, intelligence and consciousness not.
Okay, thank you very much, Eduard. Let's thank him again.
Thank you.
And now it's time for a short coffee break. So for a half an hour, I think right outside. If I'm not mixing up the schedule, then let's continue with 2 more talks at past. But for now, enjoy socialization, caffeination, and on this positive note, I think it's very good time to continue with our seminar. People are coming back from coffees. But it's time for us to begin. So we saw that the next speaker has a backup, and in case AI fails to compose music, she can do some on her own. But so the next speaker is Aljanaki, who is lecturer of AI and a data scientist here at the Institute of Computer Science. And so she also has diverse background in both academia and industry. And in academia, she exactly focuses on, well, the things she will now talk about. So please, the floor is yours, Anna.
Hello again. And my conviction is that humans do not really want to be silenced by AI. They want to be helped in creativity. So they want to have a creative dialogue with a computer. And when you talk to musicians, they usually, well, they look for a computer to somehow augment their creativity, to play together with them or to help them in some way, not to replace them completely. And so this talk will be about a dialogue between a human and a computer. So imagine talking to a robot. Well, you probably do that already, right? You interact with intelligent agents such as Alexa from Amazon Echo, or Siri from Apple, Google Assistant, Alice from Yandex, and Cortana from Microsoft. And please raise your hand who ever talked to an intelligent agent for fun. All right. Almost everyone tried it. Yeah, I tried it as well. Yeah, it can be fun. But now imagine talking to an intelligent agent in music language. So what does that even mean, talking in music language? Well, in music, there is a special type of music which is actually a conversation in musical language. It is called counterpoint. And counterpoint is a technique of writing music. It's kind of a little bit obsolete and very old. And it demands creating several independent melodies or voices. You probably heard of counterpoint if you listen to Gregorian chant or any Baroque music. And if you know who is Johann Sebastian Bach, you've definitely heard counterpoint. Counterpoint is special type of conversation in a sense that conversation is simultaneous. So you listen to several voices at the same time, not like we do in a normal dialogue. And it was mostly used in European music and Renaissance and Baroque period. And how counterpoint is different from nowadays music? It's different in that nowadays music usually has one melody, and then it has accompanying instruments that play the harmony for that melody that also agrees with the melody. And it's also a way of having a dialogue with a computer when you, for instance, compose a melody and you let a computer create chords for your melody, or vice versa. But because the other part, the chords are complementary, it's not really a dialogue. It's more like the main part and the assistant. This presentation is based on, well, loosely based on some of these papers by me and my colleagues from some other universities, and I work in this one. So for the people who cannot imagine how can you let several independent melodies talk at once, well, let's first listen to some simultaneous speech. There will be two speakers speaking at the same time and at the same volume. Try picking one and listening to them.
Imagine that somebody knocks on your door and offers to buy your house for more than you thought.
So could you understand what they were saying? Please raise your hand who could understand. Okay. I see some hands like this, a little bit. Okay. But now, simultaneous melodies are a completely different thing. Your brain has an amazing ability of focusing on several melodies at the same time. So when you will be listening to simultaneous melodies, you will actually be able to follow them. Now I will play you an excerpt from Mozart's Requiem. That is counterpoint. It will be music sung by four amazing vocalists, and they will come in one by one. And the special property of counterpoint is that they will be repeating musical material, and it will be sounding together and on top of each other. And try listening to them, and try like keeping all of the vocalists in your mind and following all of them simultaneously. So who could follow when there were just 2 voices? Okay. Who could follow 3 voices at once? Still some people, and 4 voices at once? Okay. It takes a little bit of practice, but we have 3 people in this room that could follow 4 voices at once. But for the rest of you, take heart, because we will only do 2 voice counterpoint from now on in this presentation. So counterpoint has some special rules. And they can be very strict, like in species counterpoint, for instance. There are rules that you cannot go in the same direction. So the voices should try to go always in different directions. The same direction would be, and the different directions would be. You cannot go by the interval of octave. Parallel octaves are completely prohibited, and you can immediately see why. So imagine. So because it's the same melody basically, and if you do the parallel octaves, then well, it's not separate melodies anymore. The same with the parallel quints. Well, it sounds kind of jarring, and it's also the same melody. Then dissonance is prohibited, so know this. And know this. Then what most composers did is free counterpoint. So basically all the rules are relaxed, but up to your better judgment. So you better not do this last thing that I did, but you can. And the rules are mostly based on well separating the voices, so preferring the contrary motion and avoiding the parallel fifths and octaves. And most counterpoint composers adhere to these rules. And usually there are between 2 and 5 voices, but we won't go into this details in this presentation. We will stay with 2 for now. It's the most common one, and it's easier to follow. So for short history of computer-generated music, it's very nice that Eduard did a nice introduction on the basics of how these models work. Well, for music generation, they work very similarly to how they work for text. Just you need to represent your music in some way. One of the ways is representing music as characters. So you take each note and its duration, and you represent melody as well, sequence of this character and duration, pitch height and duration values, and you use char RNN. So char RNN is the one that generates character by character. Then performance RNN is the one where you represent music by pitch height, duration, and velocity. And velocity is the one on the piano where the faster I press the piano key, the more staccato and the louder it will sound. And so, for instance, I can play something like it's very soft, and then. And these are completely the same same pitch height and same duration, but different velocity. And it gives us an ability to create well, performances. That's why it's called performance RNN. Then WaveNet generates digital samples. So there are 44,000 samples per second in a standard audio file. So, well, it generates all of them every second. And then transformers are the newest model. And in this presentation, I will be using the transformers. And now you will see why. I will play you examples from all 3 kinds of models. And you can see why the transformers are so nice. So this is performance RNN. Yeah, it is Chopin-like, trained on. So WaveNet has a very nice property that it can generate any timbres you like. The performance RNN, folk RNN, and transformers are usually trained on piano music, so they generate the piano sequence tokens, and piano is, well, very limited in timbre. But WaveNet can generate anything, and in this example, it's again trained on piano, and what it chose to generate was noise from a recording. It was an LP recording, and there was some, well, noise, and it reproduced it. And now we have the transformer by Google MuseNet. Okay, and what I said about transformers, that they basically completely eliminated all the other approaches because they sound much better, is because of the long-term structure that transformers can create for text and for music as well. So performance RNN1 didn't have any repetitions in melody. It didn't have like much repetition in harmony, and repetition and following the structure and rhythmical structure is key in music. You cannot have music without it. So that's why, well, transformers. And transformer is a model which consists of an encoder and decoder, and they were used for, well, translation. In the beginning, they were proposed for machine translation. And counterpoint can kind of be viewed as translation from the source into the output. So what I will be doing, I will be translating a melody into another melody, like this. So this is invention by Bach, and the first voice says. And then the second voice answers. And they do that simultaneously. And well, I train my transformer on multi-track contrapuntal music archive. It's an archive where each voice is separated into a separate track. It's a tricky business, actually, separating these voices in separate tracks, because usually how they are separated in a MIDI file, they are separated by hand. Well, a performer has two hands, right? So you write whatever is played by the right hand into right hand part, you write whatever is played by the left hand into the left hand part, and which voice it is, well, who knows? So in this archive, we did some tricky stuff to separate these voices into separate tracks, and to ensure that each part is as monophonic as possible, because most of this music is not for voice, which is naturally monophonic, but it's for keyboard or orchestra. Then it's not well, always monophonic. And then in available MIDI archives, there are a lot of problems, such as timing inaccuracies. Lots of these MIDIs are recorded from MIDI keyboards, and all sorts of things that happen during performance are all in this recording then. And then in Baroque music, there are things called embellishments. For instance, a composer wrote this, but what the performer plays is, for instance, this is called an embellishment, or they play a trello, like a composer wrote, and a performer goes. and that's all in the media as well. We don't want to generate that. And here are here is the contents of this multi-track contrapuntal music archive. Well, Baroque composers, as I already said. Most pieces are by Bach. And then there's Buxtehude, the teacher of Bach, Becker, Lully, and Albinoni. There are concertos and preludes, and even an opera in counterpoint. Counterpoint is a very, well, it was a very flourishing genre at its time. So, and we represent it with two different encodings. One is just the pitch height and the duration, which translates into a token. And the other one, we introduce a beat token, which is a relative positional encoding, which helps with following the meter of music. So meter is really important for music. And anyone knows what this music is? Yeah. Oh, whoever is in Estonian in this audience, this is a famous children's song about a train. Train crash. Okay, and then we take a transformer model, the very standard one. Doesn't pay off to take a bigger one because the dataset is, well, pretty small. 6 layers, 8 attention heads. Compare that to the Google's 72 attention heads. And the key to our transformer architectures are having this query, key, and value matrices. And in our case, each row of the query matrix is a token from the target phrase. So the answer in counterpoint, and each key value is from the source phrase. And then you calculate attention with this matrix operations. And here is what the model answered to this train crash song. Oh my God. So this last part is very Baroque-like, where they like go down by steps together. And well, no surprise, because it was trained on Baroque music. And here is some examples on actual Baroque music. Yeah. And more. All right, but how do you say, is it any good, right? It's difficult. So in this art type of systems, how they are trained is, well, what Eduard explained, they are trained by providing the next word and evaluating against that. But then you want to, well, have a final evaluation. And for linguistic, in natural language, there are evaluation metrics like BLEU, bilingual evaluation understudy. It's used in machine translation. It's basically comparing the contents of the computer translated phrase to the contents of human translated phrase. So you compare whether the words in these translations are more or less the same. Then there is word error rate. It also takes into account the order, and it operates on this sort of like Liebenstein edit distance, so insertions, deletions, and all that. Then recall-oriented understudy, it's about taking bigrams and n-grams from translations and comparing them. And then perplexity, it's about how how expected is the test set by the model. But all of them do not work very well for music, actually, because when you translate one counterpoint phrase into another counterpoint phrase, you don't really care whether human composed it in the same way, like you care in machine translation, because in machine translation you translate meaning and it needs to be there. But in music, you just care whether it sounded good, right? So we evaluated it using, in music, well, ways of evaluation would be subjective evaluation. You basically ask people, did you like it? Then musical Turing tests are pretty common, so you give them several pieces of music, some composed by a human, some composed by a computer, and you ask them which one is computer composed. And I think that we did for this study was a human edit rate. It was based on abuse of musicians. So basically we took a bunch of musicians, then we gave them our music and we made them listen to it. And then we asked them to correct mistakes. So here is what it looks like. It's quite easily done in Counterpoint because there are rules. And you can well, skip those rules, but you can also follow them. Here is this example of the train wreck corrected by me. And you can see that I removed the dissonance, but not all of the dissonance. Some of it I liked. And I also added a cadence in the last part. And yeah. So did I? Yeah. Okay. I'm gonna play what it sounds like now with a corrected version. Oh. All right. If you'd like to learn more about the field of music information retrieval, then there are these resources. You can take a data set and experiment yourself. You can read these books, some of my favorite ones on music information retrieval, or you can come to my course, which will be repeated some of the spring semesters. I'm not sure, probably not this one, but maybe next year. And you can learn about all other aspects of music information retrieval. There is much more to it. In addition to generating music, you can recognize scores, you can do singing generation or recognize emotion from music and all sorts of things. So thank you, and I'm ready to answer your questions.
So, thanks a lot. Who has questions? Eduard.
I wonder if in your data set with counterpoints there is also the art of fugue by Bach. Yes, it is. I don't know if it makes sense, but can you go back to the slide where you have corrected? Yeah, here. So couldn't you take some counterpoints from Bach and then, for example, generate something and then compare with what remains in there? Does it make sense?
So compare, you mean compare like you do in machine translation?
Yeah.
Compare, yeah, we did that, of course. It just doesn't work that well in music because there is so much, creativity in what could be there, and it doesn't mean that it's wrong, that it's very different. It's usually very different. Like in machine translation, you preserve the meaning when you're translating, But in counterpoint, you're not that restricted. These rules that I was talking about, they do not really restrict you. You still have, 12 pitches to pick from, and they can be in any octave, and they can have any duration, and there is so much that, yeah.
Yeah, but for example, if you restrict yourself to Bach, let's say you train only on Bach, so you expect that you generate should fit in his music, right?
Yes.
And doesn't make sense to take a part of it out, generate, and then compare with what he was really doing in his music, or it doesn't make sense.
Yeah, we did that with all these
okay.
metrics. Yeah.
And
that's what we did, and then we found that there is still so much freedom left for deviations, and it can still sound good.
So if you give to a human being music generated using the counterpoint technique of Bach, who was the main, I think, composer, the king of counterpoint, the composer will still think that this is Bach, or it's like Bach.
Yes. Well, I can play you some examples later. Come to me and I will play you and try guessing.
Okay. No, but I like a lot Bach, but I'm not a music theoretician. I know very little. I just like the music.
So, more questions? Jaak had one?
So you mentioned that WaveNet used raw audio for all of this. Are there like transformer-based approaches that use raw audio instead of MIDI input?
No, with WaveNet you have these stratified convolutions which allow you to go like really wide. But with transformers, training on a context that is that wide, imagine like you need to have 44,000 samples per second. Well, you can downsample to maybe 20,000 samples, but not to,
But using some sort of a lower dimensional audio representation would not be feasible in music?
Well, score is a low dimensional audio representation.
Yeah.
The audio, you cannot downsample it to, like 100 samples per second. That's impossible.
Okay.
Any more questions? I keep on thinking if we can take the robot arm that used to draw and just reprogram it to play the piano instead of just...
I just wanted to ask how close we are to generate songs, so music and poetry together.
There is even a Eurovision contest for that, There is a AI Eurovision contest, and they compose music, but they usually perform it by humans later. So they compose the lyrics and the chords and the melodies, and some of them are quite good. Try listening to Dada Bots.
Is there a Spotify channel for AI generated music?
There must be.
Humans are not allowed there.
But look at David Cope. Look at David Cope in YouTube, and you will see a lot of AI generated music.
So, first of all, let's thank Anna once again. And we move on to our last presentation of today by Jaanus Jaggo, who also works as the previous two speakers at the Institute of Computer Science, and he works with at the Computer Graphics and Virtual Reality Lab. And he has at least a 10 years of experience of both making indie games as well as teaching computer graphics. So, Jaanus, the floor is yours.
All right, hello everyone. Thank you for inviting me. That's right, I'm an indie game developer, and today I'm going to reveal you the secrets of making an endless world for a video game. So, how is it related to an art? I think quite well. We have moved from, like traditional art forms from digital art now. And video games are quite a cool medium for experiencing art, where you can actually they can actually immerse the people by playing the game. Oh. So and here I will explain you quite non-technically how like infinitely large worlds can be created by a computer. First of all, a little bit about my background. So in the University of Tartu, here I'm a teacher, and I'm teaching different courses about game development, game engines, and also computer graphics. And I'm working part-time, so on the other time of my life, I'm also an indie game developer, and I want to make cool game projects. I've been participating in different projects. For example, a few years ago, we had a collaboration with University of Tartu students and Tartu Art School students to make an indie game called Tripocalypse, and it was released it was a VR game and released it in Steam. And in the meanwhile, I've also tried to make some mobile games, which didn't work out very well. It's a really hard market. So neither of those games have made me millionaire. But now I'm working on my own indie game for over a year and a half now, called Plastronaut. And this inspired me to give you this talk because it uses some creative procedural generation. So, what is the procedural generation? Basically, we can teach the computers to generate any kind of content for a video game. And yeah, the computer generated content is called procedural generation. And yeah, the field of procedural generation is really wide. As far as our imagination allows us, we can pretty much let computers generate anything, starting from music, different art forms, to story, and even to the gameplay. So here are just some examples of different type of things that can be procedurally generated, like different aliens in games like Spore, or characters in The Sims, for example. And here are some more procedural generation examples. We can there are games that generate galaxies, and the main benefit of having a procedural generation system in a game is about its fantasy for the players, that they can like pretty much play it for a long time. It has a lot of content, and yeah, every time they play it, it's a little bit different. But of course, there are some games that step even further and are generating the full game worlds, in some sense, in sometimes infinitely large game worlds, procedurally. So we all know Minecraft. We know that people are still playing it, even though it's over like 10 years old. And recently, a few years ago, No Man's Sky was released, which where the whole like galaxies and like billions of star systems were generated, and all the flora and fauna in these planets. And yeah, so now I'm hoping to also add the Plastronaut here, which is not a 3D game, but it's a 2D mining game where the player can like dig really fast, really quickly through the environment, and it needs a really large world for that. And it's just not feasible to handcraft such things. All right, but all those, so technically, they are none of these games are like really like infinite in that sense. There are some technical limitations from computer science. There is just a limited precision of numbers. All those words still have an end, but for the players, this end is so far away that it's just not feasible or reasonable for them to get there in a normal time span. So, what's the secret of creating such a world? The secret is to make the generation deterministic, so that and make it make it possible to calculate any location in the game world by just knowing the location itself. So then the game can reveal the area that the player sees and not calculate anything around it. So yeah, in all of those games we can ask from the game, well, in this position, what should there be? What should there be? So in Minecraft, there can be a mud block. In a No Man's Sky game, there can be a strange alien plant, or in Plasternaut, there can be this two-dimensional mushroom. So, all right, let's take the easiest example. We have the two-dimensional location, and we want to know what is in there. Is there this mushroom or something else? So, where should we begin with? First of all, let's just generate some randomness. Let's assign it randomly. And moreover, we don't just want like pure randomness, but we want to make it look random. So it's still deterministic that every time we point at the same location, we want to know that there is the same mushroom, which allows us to ask this question pretty much. And the kind of function that does that in computer science, it's any hash function actually. So we just need a good hash function for that task, to take in the coordinates and give out some random looking stuff. And we don't need a cryptographic hash function. It doesn't have to be like secure and non-reversible. But it has to be really, really fast to calculate, because we want to calculate a lot of. We want to calculate the game world really quickly. So, like the common randomness functions, they just take the arguments, multiply them by some big prime numbers, and then apply some cheeky bitwise operations to make it look for us, for humans, to look kind of randomness, scramble all the bits together. So for this particular location, the output number can be this large integer, for example. All right, we have some randomness. How can we use it to place the mushroom? We probably don't need all of the randomness. We can just check the last digit, for example, and define some threshold. If it's larger than 5, then place a mushroom. Then it has kind of 50-50 chance to appear there. And by doing that, we get this kind of placement. So yeah, it appears quite random. We can change how frequently the mushrooms will appear, but it's not really interesting. It's a noise, and it's also actually such functions are also called noise, which yeah, this is like a computer science definition of a noise is a function that gets input as of a coordinate and produces output, say, a pseudo-random looking value. All right, but there is little we can do with such noise. Maybe there are some better noises. Let's take a look at this one. This actually looks quite similar. It's called a simplex noise. It's like a blurry version of the previous noise that was the white noise, and it relies on the same sort of like simple hash functions to generate the randomness, but just like blends it together to make it look smooth. And with that kind of noise, we can already do something. So, for example, we can generate it for different coordinate scales. We can scale the coordinate systems and generate different frequency noises and then mix them together. So, for example, if any of you have used Photoshop before, there is the filter generate clouds in Photoshop, and this is exactly what it does. It generates multiple layers of this kind of noise and blends them together to get this cloudy-looking output. All right, and now this is a little bit more interesting already, so we can do stuff with it. We can, for example, threshold its value. So define some of the darker values and some of the lighter values where we place the blocks. So from some grayscale value, everything that is darker is an empty, and everything that is lighter should contain a block. And now it kind of represents or reminds us caves, maybe cave like structures. And yeah, we can use it to place like solid or non-solid blocks in the game world. We can also use its grayscale value to like color these blocks differently, make some of the blocks that are inside the groups darker and other blocks lighter. And we can use another noise layer with a different frequency combination to add holes to the background. And yeah, that's already looks nice, like some underground cave structure, and that's what Plasternaut does. But still, what about the blue mushrooms? It's something where you can wander around, but if you can't really find something significant, there is no point to go there. So there are different ways to add them. We could just scatter them around uniformly with a hash function, but that wouldn't look really nice. Instead, we would prefer if like the different mushrooms are grouped together in certain locations, so then it would look nicer. But in addition to mushrooms, there can also be other types of objects. There are like hundreds of different minerals and items that you can find from underground. And if we calculate like a more complex noise for each one of those objects, it can get really slow. You can't really calculate it in real time for the player. So just using several like layers of simplex noise is not working. But there is some other computer science construct that can be applied. So I know many of you are aware of Voronoi diagrams. So basically, this is a method for partitioning a space into cells. The definition is quite simple. You just scatter randomly a lot of seed points in this space, and then all the cells are defined such that the points that are contained in the cell are closest to its seed point, and and this way all the points are like grouped together by distance. And yeah, theoretically, to generate such diagrams for any kind of like cell distribution is quite can be quite computationally complex. You might have to like if they're like really randomly scattered, you need to like compare the distances for each cell. But for simple applications, when if they are like very uniformly scattered, we can just compare the neighbors and do it quite quickly, calculate it quite quickly. And the Voronoi noise, it's also used often in other art forms. A lot of artists like to experiment with them. There are some sculptures that like real big sculptures that use Voronoi patterns to make them look interesting. And yeah, here's for example an example how a 3D mesh can be destroyed into pieces using the Voronoi. Yeah, you can use it either in any dimensional space pretty much. But because it's for a simple point distribution, it can actually be calculated also in as a noise, and this kind of noise is called Worley noise. But the great benefit of this noise is that it has two related outputs. First of all, we can output the cell IDs with we can just assign random values for each cell, and secondly, we can also get the distance from the seed point. And by combining them, we can select some of the cell IDs, also select some distance radius, get the union of them, and place certain objects into those exact locations. And we can repeat this process for all the different types of objects. We can just select different cell ranges and place some other objects in there. And yeah, this allows to pretty much with just one noise computation place any number of objects into the world. But yeah, just assigning them into regions and placing the objects. To make this look to run on the computers in real time, the world can't be like the whole world obviously can't be calculated. Yeah, it's infinite, so so that won't work. So instead, only the regions around the players will get calculated. But usually it's shifted just enough outside the screen, so the players won't notice it. And this calculation can also be done in multiple steps. Sometimes to place some of the objects like mushrooms, it needs to calculate. It needs to know whether it has a solid block beneath it or not. But yeah, this all can be calculated deterministically, or if it's done in multiple iterations, then in the first iteration the solid blocks can be determined, and then the second iteration can place the scattered items around. And then to create even more interesting layouts, the world can be made out of different biomes that are basically just a different set of tiles with different rules to place them. And the biomes are also distributed with Voronoi noise, just with a much larger scale. And yeah, with this kind of game worlds, it can be a little bit more exciting to explore for a while. But it still can't compete with handmade levels. So handmade, human-made game worlds are always more interesting because there is this human creativity, human touch. And even like No Man's Sky, that's been developed for many years and by a lot of developers, it still gets boring over a time when the humans start recognizing the same patterns, even though many more things are procedurally generated in there. However, a quick fix for that issue is to combine it with handmade or human-made templates. So, for example, in Blasternaut, there is the in-game editor where a template structure can be made. And these kind of templates that are human-made can be scattered around the world and create some unique locations to find. This is, for example, how the template itself looks. It has some specific blocks to blend it with the rest of the game world. And this template system, for example, was made of one of previous year bachelor students as a bachelor thesis. So I think it was quite a good work. He got an A. And yeah, this is how different types of like human-made templates can look in the world. There can be like machines or bunkers or ancient ruins to find and add some human touch to it as well. And now, I don't know how much time I have left, but to actually see how the game world looks, I would like to show you a little video about how the game looks and is procedurally, look in the real game. So, because you have some really explosive tools, you can like mine stuff in this game really fast, and that's why I need really large game worlds. Yep. So yeah, the game is still in development currently. I'm still working with different students and adding cool computer science, applying computer science technologies to make it really fun. Yeah. So thank you all for listening. I hope it was interesting to learn, to hear. And now let's give you some questions. Also, I have some exclusive Blasternaut mini figurines, 3D printed, the ones that were destroyed earlier. So those people who ask questions will get the exclusive figures. I think it can be motivating. Thank you.
Thank you, Jaanus. Can we mute the video? Yes, and well, game's on. Who has questions? Wow.
Okay, I guess I got microphone already.
Go ahead.
Okay, I have a remark and few questions. Remark is that you're mentioning Voronoi cells. It was quite heartwarming because, well, I asked my students to draw them at my solid-state physics course, the dots being single atoms, of course. And the question is the concept of cellular automata used in these things or approaches?
Yes. So also I'm considering using cellular automata in Blasternaut as well. I have proposed one of the topics about it, and like the main thing that it can be used, it can be used to simulate like the physics of blocks and make them like make some sand fall and I'm planning to use it for simulating water. So you can like make the water out of little cells and simulate their movement in the world.
And one more question, if I may. Some people believe that we are living inside a huge computer simulation or computer game. What do you think about this idea? How can we check it? And taking that this is a case, how would you evaluate this game? Well done or need some improvement?
Well, real life is definitely quite boring often. I think it can be better made, but well, our current current knowledge of computer graphics don't allow us to make like everything yet. Although the newest models can quite like cheat the eye. So the recent graphics like looks quite realistic, and in some cases you can't really tell it apart if it's a real human or computer generated human, for example. But yeah, I think it's overall it's a larger theoretical questions whether we are living in a matrix or not. I will leave it up to everyone to decide.
Thank you. Next question there.
Thank you for the nice presentation. I have two questions. The first one is about the way you generate levels. So the question is, with that random procedure, pseudo-random procedure, you're creating the environments, and in case of your game, the environment is destructible, like the character can explode its way through. Let's imagine the world was not destructible. Is there already a way to create a level which at the same time automatically solves the feasibility problem? Like simply imagine the case of from point A to point B, it's feasible to reach. There are no like blocks. Is there something that at the same time solves this feasibility problem as well? That was the first question. The second one,
let's stop for the first question. So, what feasibility problem exactly? So, where the problem comes?
So let's take the simplest form. From point A to point B, it should be reachable. Like a point B, like a castle or something. So we created the game board, and the road will be generated automatically. But with this way, at least the way I understood it, there's no guarantee that between any 2 points there will be.
Yes, so that's actually a big problem with such work generations, that you can ask it in one way. You can ask what is in this location, and calculation just gives you the answer. But you can't ask where some objects are. And the same principle pretty much is also used in crypto mining. So in crypto, in crypto mining, I personally don't like this concept. It's quite wasteful. But what they are doing is that they can't ask the other way around. What is the hash function that has a certain property? They need to calculate a lot of hash functions to find out to find this very rare hash function that has a certain look. So and here we have this exact same problem that we can't just ask this opposite directional question. And if we want to add a road to the game world, we need to do it just using this one way calculation, which or something tricky that simulates that. And that's the same reason, for example, why rivers in Minecraft are also only assigned at the edges of biomes. So that's like a convenient location where they are, and oftentimes they are looping around because it's a really hard problem. There might be some clever solutions for that, but yeah, I think it's a hard question to answer.
But I think actually giving your player a blaster to ensure feasibility, and so if he cannot pass through somewhere, he just blasts his way through. So that also removes the problem in your game.
Yeah, exactly. The player can destroy everything in this game. So
you had another question.
I also have a lot more about this question, but later. But the next question is, do we already have software or like algorithms that deal with higher level concepts, like automating the procedure of creating like missions and objectives and stuff like that, to have like different variant of the same game with like kind of different missions?
Yeah, I don't know any game that like does everything at the same time. So the workload like increases exponentially as you add more layers. However, there are some games that are procedurally generating puzzles, for example. Like they are using, for example, some formal grammars to make different puzzle rules and then combining them to start from a simple puzzle blocks that are trivial to solve, and combining them with each other to make a more complex puzzles. About the mission generation, I don't know, don't have any great examples right now.
Thank you.
So, who else?
All right, and afterwards, those persons, please come, and I have several Plasternaut figurines.
Just remember that 2 questions doesn't get you 2 figurines, so you can ask just 1 question.
The mic is not working, well, I'll just talk like that.
Yeah, all right.
It should. Is it? Can you hear me?
It's on. Yeah. It's fine.
Yeah. Hello, can you hear me?
Yes.
It's the first time speaking in the mic, so it's really exciting. My question is, like, I've been playing video games for a long time, like since even before I was born, I was just playing video games. So, like, when you are developing a video game and there's a level that's randomly generated, how do you make sure the player doesn't get to a dead end where like the player just can't get ahead, like the objective can't be reached? How do you make sure?
That's the first question.
Yes. So actually, well, in Plasternaut you have the blaster, and you can just dig your way through the game world, and most of the games that are doing like really infinite game worlds provide similar tools to like get rid of this issue. However, I've actually tried to make this another procedure generation system before. And there I wanted to tackle the exact same issue. I wanted to make a game that's procedurally generated, and the path is kind of linear, where you can like always move from point A to point B, and you don't have to like wander, get too lost in the way either. And how I solved it, I have some good examples in my courses that I'm teaching. Is that I took the inspiration from Connect the Dots game. These are the newspaper games where you have dots and that have numbers, and you have to connect them to make some image. So I simulated a very similar thing. I created this kind of like random walk in some area from point A to point B. I got the path, and then I added a lot of these different noises and modulations on the path to make it look like random, but still retaining the pathway from A to B. Yeah.
Cool. Just one more question, if you don't mind.
Short.
Yeah. So, like, when I play video games, the thing that I hate the most is, like, when I played Witcher 3, the campaign ended. Like, it was just amazing. Do you think the campaigns, like can they be randomly generated? Like, the voice acting and the story, basically, do you think it can happen in future?
What exactly to generate?
for example, like stories, like the game generates itself the story, the voice acting, you know, the everything. Like just consider Skyrim.
Well,
or Witcher.
I think it always already generates a lot of research topics. I know that in Dwarf Fortress game, for example, this is a very old game that's like that's simulating the dwarf colony. They are like procedurally generating like histories, different before the game begins. It just generates like some dynasties and kings and fights that have happened in the past, and based on those events, it like has kind of like a lore for the game. So yeah, they're doing something similar, but yeah. I personally would like to see like games that create like really or any procedural generation like systems that can really generate like new books, like new Game of Thrones style complex intrigues and plot lines. It would be cool, quite cool.
That's called GPT-3.
Actually, my question is really similar to previous one. I wanted to ask if there are any games that can compute complexity of the level depending of players' behavior before. So, or for some reason, the complexity of level should be manually planned for each level.
I don't have any examples about like level getting tougher when you play it too well, and yeah, that's also a nice idea. Typically, most games are doing it in a very basic level. So in like shooter games, they have some certain like built-in rules. So for example, if the player makes too many headshots, then the enemies can start carrying helmets, for example, or like adjust with the playstyle a little. But yeah, I haven't seen any procedural stuff in that regard.
You can probably check a game really easily by playing really slowly and simply, and so the game will be easier. Any more questions? It doesn't. Oh yes, please.
Thank you. So I was wondering, these agents in your game, they are like moving in a three-dimensional world. They can turn around, yeah, as if there was a third dimension. But the obstacles, they are like in a two-dimensional world that one cannot go around them. One can only go through them. Have you thought about this?
You are referring to the aliens who are walking around in the game world, or
the one that you were showing here.
What exactly? Can you explain a little bit more?
Those agents who are shooting at the, I don't know, rocks or whatever they are. They can turn around, like shoot on that side, then turn around and shoot on the other side, right?
Okay.
So. So there must be a third dimension for them. Because in order to turn around like this, there must be a third dimension. But the rocks themselves, I mean, usually in the real world we can go around a rock, we don't have to go through a rock. So it's as if the rocks are only in two dimensions, that you cannot go around the rock.
Yeah, so that's the magic of making a 2D game. That well, pretty much anything that can be like displayed can be yeah, anything that's like that the human can see, you can just place objects however you like. Now, obviously. It might not be accurate in the third dimensions, in that sense that if you imagine this game world as there is some depth to it, then yeah, people can go around some rocks and such. But overall, like the constraint of having a 2D game, it has some benefits for the gameplay. It makes it easier for the players to see and mine. In a 3D mining game, you are more in a more claustrophobic game world, and you usually can only see in front of you, and yeah. So there are some pros and cons of having this fake 2D game. But about the agents, another student last year developed aliens that were walking around in a video, and it was also quite challenging task how to make them actually not get stuck in some places, because the world is like really hectic, and it's and we made some quite interesting solutions to make the enemies to crawl around on those messy blocks, and yeah, they can also walk on the 2D walls and on the ceilings, but currently can't get through them yet.
I was really hoping you would have answered that it's the fault of the 2D screen, that the agents turn around, we just cannot see it because of the screen limitations. As soon as we get a 3D holographic screen, then we can see it. Okay, so this is a perfect time to finish today's seminar. First of all, thank you very much to today's presenters. So Jaanus, Anna, and Eduard. Secondly, thank you very much to all the organizers and technical support and camera crew and everyone who made this event possible. So thanks a lot. Well done. And finally, let me invite everyone to the next data science, webinar or seminar. We're all hoping it will be a seminar, which will be titled Federated Learning, the Future of Edge Intelligence is Now. And this is to take place on November 18th at 5. And, well, judging by this slide, at least, it's going to be a webinar on Zoom, but stay tuned. Some info will follow. So, last but not least, thank you to all of you for your attention and questions and participation. Thanks a lot. So, this is it.